So let's get started. So thank everyone for coming and joining online. So it's my pleasure to introduce today's speaker, Professor Jian from Duke University. I met Jian in 2017 when I was leading the Statistical Association's section on statistical learning and data science, and he just became chair of the SIGKDD, a section that data mining. So we exchange ideas to see how we can create more convergence between the CS community and the statistics community. So I was very glad that he accepted our invitation to speak about his research on data valuation in federated learning, but he is expert in many things, as you can see from his bio, that he has rich experience in both academia and the industry, and have led large corporations and also large professional society. Now he's leading a large department at Duke. So with that, it's my pleasure to give the podium to Jian.
Thank you. Yeah, thank you, Mark. Thank you for having me here. Today my talk may not be immediately related to environment and climate, but I will introduce one of the research I'm pushing hard on data marketplaces, and also how it can be combined with machine learning. Oh, okay. So I'll talk about what data validation is and what data validation in why data validation is federated learning. And then I'll talk about data validation in federated learning, what's the idea and techniques. And we'll also talk about how to do the personalization in federated learning. So I hope people here more or less have some ideas about federated learning. Federated learning indeed is a very simple application scenario. Is that, well, if we have multiple parties, for example, we have multiple banks or multiple hospitals, and then they have data about one thing. For example, multiple hospitals, we try to understand what's the effect on COVID on patients. But of course, the hospitals cannot share their data. So, and they don't want to share the data because they're from privacy issue and business issue. So how about we build a mechanism so that we can train a model in some way so that each party doesn't have to release the data, but we still can get the model. So that is what federated learning does. And in a nutshell, the idea is very simple. Well, we take these into iteration. In each iteration, first of all, we randomize a central model at the server. And then in each iteration, the server will send the model to every party. And every party will say, no, this is not the best model according to my data. So from which direction the decision boundary should change a little bit. So I make a proposal, make a suggestion. And then the server will collect such feedback and then do some, based on some, for example, linearity of the model, to do some kind of aggregation. For example, average out all the feedback from the parties. And then we'll get hopefully an improved model. And then we will send this improved model back to every party to say, how about now? And then the party will, everyone will check against its data, say, it's a little bit better, but not good enough. Indeed, it should be in that direction further. And then we iteratively collect data and then to do this. And hopefully, after all, it will converge into some stable stage and may not be good for everyone, but hopefully it's good for the union of all the parties. But in this whole process, as you can see, each party only releases the information about the suggestion to the model, but does not release any information about their own data. So that's what the federated learning in a nutshell. Federated learning, there are two kinds of federated learnings. One is called the vertical federated learning. Essentially is that, well, each party has the complete set of features, but just say they have different entries. For example, the example I gave about the hospital is this case. Each hospital have the data about their own patients, but on all features. But different hospitals have different patients. Or we may have the horizontal federated learning. Essentially is that, well, each party has the data about all entries, but they only have some of the features, but not all the features. And there are some kind of identity assumed so that such records can be connected. For example, the social security number or some kind of ID that can collect them. Okay. So we can conduct a federated learning in this way. Federated learning is a very, very hot topic, and indeed, I guess I'm underestimated the population of research there, and at least thousands of papers have been published in this area. I do a very simple count in KDD 2023, which was just 2 months ago. There are 23 papers on that. And in Neuro IPS, we know one of the flagship machine learning conference last year, there was at least 40 papers on this topic. And I did not get access to the papers this year, so I don't know. But it just gives you some, data points about that. However, from the industry point of view, there's very, very few real implementation or application of federated learning. Well, there is a very good report on that. It says, despite vast research efforts and potentially large benefits, the federated learning are only applied really in practice, and only in those applications reported. Most of them are still within one federation, institution. But wait a minute, if you are within one institution, why do you need federated learning? Because you just can, the CEO just write an order, say, put all the data together, otherwise you'll be fired. Then you get the whole data set, right? And, well, people all understand why federated learning is hard, because although in this whole process, we say, well, it is, you don't release the detailed data, so it preserves the privacy. But wait a minute, you still make the suggestion on how the model change. That may imply some kind of your data distribution, right? And therefore, there's still privacy concerns. And so far, there's no theoretical guarantee on the privacy. Essentially, is that there's no written mathematical statement about what is the maximum amount of privacy that the federated learning may leak. And another important thing is that in federated learning, we always assume there's an agreement among those different parties, so they are very willing to share the data. But wait a minute. I mean, who wants to share the data without any compensation, right? That's a big issue. And one underestimated reason here is that the fairness among those participating parties in federated learning is not addressed at all in the huge body of literature in federated learning. And you cannot simply weight data as you buy apple in grocery store. The party having more data records contribute more? Not necessary, because a lot of such data may be redundant in terms of statistic distribution, and they do not really contribute to the real performance of the model. But some parties, they just got very few data records, but those are very important records. And then they may contribute a lot to the final model. And this is not touched in the research. So federated learning essentially is a good thing because it enables multiple actors to build some common machine learning model, robust machine learning model without sharing data. But it also leads to some questions. For example, how are the contributions to federated learning recognized and compensated? Because without compensation, data sharing is hard. In some situation, for example, like open data in government, yes, you get the data for free, but don't forget it is not ready for free. The taxpayers pays the effort. Okay, and in many business application scenario, indeed, the compensation is so important because the data represents the effort. When you collect the data, when you clean the data, when you label the data, it takes time, takes human effort, takes electricity, takes water, takes computation power. And another important thing is that one company's data is its business advantage. And you ask the business players to give up their business advantage. This is not sustainable, right? And therefore, for what scenario is the another important question is that, well, we have many people work together to build one model. And we know one thing for a long time is that in many situations, one size doesn't fit all. So this one model may not work for everyone. Indeed, in many situations, particularly in public policy, one model doesn't fit anyone. But just say aggressively, that's the most that's the best trade-off we can stay with, right? So therefore, in what scenario is the common model optimized? And there are also some economic consideration of those participating parties. For example, fairness in rewarding for each participating party. So how we should give the compensation according to the contribution, and also the fairness in learning outcome. By the way, here I talk about fairness a few times, but they may carry different kinds of fairness. One is that when I contribute data to this whole process, the fairness is that everyone should be compensated according to their contribution. Another thing is that, well, once I get the common model, and then the common model should benefit me, instead should not be against me, right? So I should have the fairness there is that everyone contributing should get the fairness in effectiveness of the final model. If not, I should be compensated in some other ways. I know the model, after all, is not good for my data. However, I should be able to be compensated by some other means for my, investment in the training this common model. So why is the fairness in rewarding very challenging? Because we need to evaluate the value of the data in the federated learning and assessing the contribution of a participating party towards the outcome model. This is not that straightforward. Okay. But there's some approach to do that. And if you are from machine learning, then you immediately come up with this idea. Yeah, that's easy. We can do leave one out. Essentially is that we train the model twice. The first is that with your data, and the next time is that without your data. Then the difference should be your contribution to the model, right? However, if there are n participating parties, then we need to conduct the federated learning at least n times, right? Because you need to take out one every time. And typically, federated learning only goes once. And those parties won't allow you to run federated learning many, many times because it's very costly. And also, you need a lot of synchronization among the multiple parties. And by the way, I just give you a nutshell in federated learning, which is wrong. Sorry about that. In real federated learning, in each run, for the interest of efficiency, we don't ask everyone to submit their proposal to the model for two reasons. First reason is that it involves a lot of complication, and we try to reduce the complication cost. The second reason is that some people may be extremely slow. They never return the answer. Then I cannot just keep waiting until I collect the answer from everyone. Therefore, in implementation, this will be done in the following way. I randomly select a subset, ask you for proposals. This is just like voting, and why we need the representatives to discuss in the Capitol Hill, and then decide that we still can run the government for another month, is that we don't have time to ask everyone in this country whether you agree or not, right? Another thing is that we don't wait. We set a deadline. If you don't submit, then that's it. We don't consider your input. Then the leave one out just doesn't work, because you even cannot collect the performance without your data, because your data may be excluded for many different reasons. Okay. So it is impractical to ask a large set of inter-organization parties to run federated learning many times under different configurations. The configurations are just cannot be controlled precisely in this way. Okay. So one idea to, as we say, the leave one out method may not work very well. One idea is that let's talk to the economics. Economics are very good in designing such fairness framework. Yeah, indeed, there is one well-established measure here is called Shapley fairness. You say federated learning is fair if each participating party gets the fair share of the revenue produced by the outcome model. Okay, straightforward. And Shapley fairness essentially is the work winning the Nobel Prize. By the way, congratulations to Columbia winning a Nobel Prize again this year. Yeah. So what they do is that, well, if we have K parties cooperatively complete a task, and it leads to a model of value V. Let's say we have a utility of the model, then fairness should be addressed in four perspectives. The first is that it should be balanced, meaning the value V should be fully distributed to all parties. It should not be someone holding something not distributed. The second is that symmetric. If I have two data sets, A and B, these two data sets have the exact same contribution for every collaboration, then A and B should receive the same compensation, well, which is intuitive. The third is a zero element. If I do not make any contribution to the model, no matter I contribute the data or not, I should not be paid. There should not be any free ride for this whole process. And also should be equitable, meaning if we have the same set of contributors training the same model, but this model has been used in multiple tasks, and then simply their shares should be just a summation of their gains in each task. So Shapley introduced one measure, is called Shapley value here. Essentially, this is the expectation of the marginal gain of this S when this S participates in the collaboration. And it has been shown that the Shapley value is the only measurement that satisfies all the four requirements here. So that is well established. Now, let's just use Shapley value in federated learning. The challenge is that in order to calculate this, as you can see, we need to try all the possible combinations. Now, the problem comes back. And in order to compute the Shapley value, we need to run federated learning many times. That's just simply unacceptable. Even you use a Monte Carlo simulation, that's still not acceptable. What we want to do is that we run the Shapley value, we run the federated learning once. We get some kind of measurements. That's the requirement. Okay. So this sounds mission impossible because you try to reduce the number of tests from exponential to 1, not 0.1. 0.1 is a constant, but this is exactly 1. There are some very few tries before, for example, the federated Shapley value. The idea is that in each round of training, we try to compute the Shapley value for all the parties. You can use the performance gain as the utility, for example, and then you report the summation over all the rounds as the final results. And well, the advantage of this approach is that it doesn't require model retraining, and it retains some of the properties listed by Shapley fairness. However, federated Shapley value has some drawbacks. First is that in order to reduce the complication costs, many widely used federated implementations will just do the sample in each round. We know that, right? And this just doesn't work for the federated Shapley value because it assumes that in each round, all the parties should be consulted so that you can calculate the Shapley value of each party in each round. And then you can sum up their contribution at the end. And if for, sampling issue, concern, some parties are not given the chance to provide its feedback, then of course it loses its Shapley value in the final round, in the final result. So that's not good. And so there's a lot of complication. There are lots of some studies about the unfairness in this design. Okay. How can we solve this issue? One idea we do is that we propose a revision of the Shapley fairness. We try to trade off between the fairness and the efficiency. So we propose this so-called epsilon Shapley fairness. Is a relaxation of the fairness of the federated learning. Essentially, we still do, instead of doing 4 things, we only do 3 things. First is epsilon symmetric. Essentially, is that if these two have the same contribution, instead of requiring them to get the same rewards, we say the rewards should not be larger than epsilon. So we give them a range. And also, we allow a little bit about the free ride. If someone doesn't make any contribution, we still can give them up to epsilon compensation. And also the epsilon additivity is that, well, when we have multiple tasks, then we can allow them to do the summation up to an error of epsilon. And we do not require on the balance for obvious reason, because when you allow this epsilon, then when you sum those all those things up, they will not be the same as the utility after all, right? And you cannot really control how much loss you will. But empirically, we show that the loss is very small. So this parameter epsilon is to control the quantitative requirement on the fairness. If you allow a large epsilon, then you say, I don't care about the fairness that much. If you allow the epsilon to be very small, you are stick to very strict fairness. Now, the idea is of our problem is very, very different from the traditional Shapley value calculation. We formulate it as a matrix completion problem. Why matrix completion problem? We just consider such a matrix is T times 2 to the power n. 2 to the power n is the number of possible combinations of the players. And T is the number of runs in your federated training. And then it's a very natural setting is that each entry is what's the contribution of these subset of players in this run. Okay. And of course, if we can compute this matrix U, we can obtain the fair Shapley value for every subset of clients in every run. So Shapley value computation is can be obtained straightforwardly. And however, this matrix, of course, you cannot observe the full matrix, right? Because in the central server randomly select a subset of T in each run, only a very small number of the entries in this matrix will be observed. Okay, and the problem is that we observe a very sparse matrix here. Can we complete the whole matrix? Okay, is that understandable so far?
So yeah, one question: what exactly the fairness Shapley value is? I can understand the epsilon fairness assumptions, but yeah, how exactly that assumption is connected to the fairness?
You can just sum up, for example, all the contribution in all the rounds.
Oh, I see.
Okay. For example, yeah.
Oh, I see.
Okay. Good question. Yeah. So now the intuition here is that, well, let's call this matrix as let's call this matrix as utility matrix. Okay, it records the utility. We claim a utility matrix should be approximate low rank. Why? The intuition here to make this assumption is that, well, if two parties have similar data, their contributions should be similar, right? And also, in two consecutive runs, the parties with similar data should have similar utility, right? And therefore, you can imagine is that when you get the collection of different subsets, and the utility function will change progressively. And in consecutive runs, their value will be similar. And if two sets have similar data after all, and then they will have similar contributions. Okay. And we also have empirical evidence showing indeed this works. I mean, in view data sets, indeed, it's rank, the singular values distribution, only very few have high singular value. Most of them will have very low singular value. So the problem is that how can we approximate? How can we formulate the approximate lower rank? Let this be a matrix and epsilon be a tolerance threshold. The epsilon rank is given by these submatrix in this matrix, such that you try to change some values in the matrix such that the rank of the matrix is minimized, so that the difference between the two matrices is at most epsilon. That means you have a matrix, and then you try to change some entries in this matrix. For each entry you change, the change cannot be larger than epsilon. You try to make such a change so that the matrix after change has the lowest rank. So that is the low rank, epsilon rank. And This K is the epsilon rank is the smallest integer to satisfy this condition. So we get the one result is that the epsilon rank of the utility matrix is of order log t, where t is the number of iteration and is independent of the number of the participating parties. So that gives us a very good promise, because now the problem is reduced to only related to the number of iterations and not related to the number of parties, the players. Okay. Oh, sorry, I think right here, probably the formula here, due to machine capability, they have messed up. So essentially, we say we can reduce these into this is a specific form of a result of what I say here. So essentially, that gives you the concrete formula of what I mean by is only related to the number of iterations. Yeah. And also, we can guarantee the major result, the fairness there is that it is using this mechanism. If we can, complete the matrix, and then the epsilon can be set into this parameter. Okay. So that's what we do in the that's the algorithm to complete the matrix. Essentially, what we do is that we have multiple clients. In each client, we collect we conduct the federated learning, and in each iteration, we collect the matrix, the information to populate the matrix. We have sparse matrix, and then in this matrix, we essentially only need to solve such an optimization problem to complete the matrix using the factorization, so that after all you can get the result. Yeah.
So one another question. So in each round, how did you select the subset of the parties?
Oh, okay.
Do you select it randomly, uniformly, randomly?
This is a very good question. Indeed, it depends on different algorithms. For example, some algorithms would take a greedy approach to say in the previous round, which parties suggest the largest change of the model. For example, if the one just say, oh, the current model is good enough for me, then I don't need to ask you again. Yeah.
Oh, I see.
Some is that, for example, using boosting. If the current model of the test data set is, if the reported model change is marginally the largest for this client, then you may ask this client again. And there are tons of studies on different policies in the selection of subsets. Yeah. Okay. And what I say here is about the vertical federated learning, and we can extend this to horizontal federated learning. We can extend it to vertical federated learning, because in vertical federated learning, indeed the situation is different. Now you have all the entries, but you have different features. Okay, so I won't go into detail. The major idea is major concept framework is the same. We still do the matrix completion, but the technical details are very, very different, because now that what you're missing is the features instead of the records. So we talk about the first fairness here is that, well, when you do the contribution, and then how can you evaluate the contribution to the final model? Let's look at the second fairness issue, is the fairness in learning the outcome. Is that, well, we train one model, this model may not fit all the parties at the same in the same degree, right, to the same extent. And can we make it fair? It's unlikely because you can only produce one model, right? And then if this model treats A better, it may have to sacrifice B, right? How to solve this problem? Our idea is that one size cannot fit all. Let's do multiple sizes. Let's train multiple models. However, when we train multiple models, we still want to run the federated learning only once instead of running federated learning many times to fit many models. And another challenge here is that how we can look at this one model, whether it fits A or fits B. How can I get this kind of information? Okay. So this becomes a personalization challenge. Personalization in federated learning is difficult, it's not easy, because you want to protect the data privacy. So I cannot tell you which model fits me better, because that leaks my privacy, right? And personalized models is that of different kinds to produce, you want to produce a good results for every client. And also, implicitly, if you want to do that, indeed, you try to customize the collaboration process. Okay, and our idea, I mean, there's some related work on that. For example, the Fed average and the essentially this one doesn't do any personalization. Fed props also don't do any doesn't do any federalization. Project is another approach. Each kind has a personalized model. Essentially, each one trains a model, but takes some data from the others. But that's a little too many, and also it is unknown what's the advantage of this model. Okay. So we propose a new idea here. Let's forget the technical details here. The idea is very simple. Indeed, when you make proposals to the model, I get some feedback from you. If I want to train K different models, one thing I can do is that I can do some kind of a K-means clustering on the feedback you provide to me, right? And if A and B have similar data or have similar feedback on the data, and then they will make a similar proposal to the model. And using this similarity, I can identify, yes, maybe I can train a model, give more bias on A and B's feedback. And using these, combining many parties and different, using some kind of a K-means approach, we can form K models, and one takes a weight to be preferred, something like a topical model in statistics, and then take a weight to say, indeed, I should learn that model better. So in that case, we sort of like do the optimization for this. And here, essentially, if I train M models, I just initialize those parameters here. And then in each iteration, I use kind of the K-means ideas to optimize the parameters, update the parameters. Okay. So, and also we still can claim that this revised version will preserve the privacy at the same extent, as the centralized federated learning, because they only disclose the same amount of information. They do not disclose any further information than the proposal of the change of the model, central model. Yeah, this is the optimization function. Essentially, for each one is that we can, rely on the private data on the client C, and the client C gives the feedback to the central cloud server, and then each client carries a weight. These weights will be learned in this whole process using something like a k-means, so that they will be similar if the two clients have similar distribution, and then they will subscribe to the model with a similar weights. Okay. So the collaboration is through using those parameters, those weights to the models. So I'm almost on time. Is that essentially I talk about the learning outcomes and rewarding fairness are two important fairness in federated learning, and they have not been addressed systematically so far. And we push the data valuation in federated learning. We try to use these to address the rewarding fairness. And also we use the personalization to address the learning outcome fairness. But there's still a lot of challenges and opportunities here. For example, one simple thing is that, well, how can we set the parameter K? How many models do we need here, right? And because each party keeps its own data, and there's no sharing among them, so we have a hard time to estimate the number of models that should be needed. And also in this way, in our model, we still cannot provide any quantitative guarantee on the quality of the personalized models. Some models may serve their own group better. Some models may not serve their own group better. Okay, and we have not considered data poisoning in this whole process. Data poisoning is such a process. Is that I'm a bad guy, but unfortunately, you include me in the federated learning. So I just keep providing bad data, trying to destroy your final model. And then there's some work to detect the data poisoning in federated learning. However, once you do personalization, it is unclear how to detect this and how to what extent I can decide your data is poison or your data indeed is just some extreme bias, extreme cases of the distribution. So this is another very interesting direction to go. That wraps up the talk. I'm happy to answer questions. Thank you again for having me here.
Just a quick question.
Yes.
Just a quick question. So you mentioned that each client has their own weights on the model. So where is the collaboration part? Because without collaboration, it's more like federated learning stuff.
Yeah. I mean, first of all, when we talk about collaboration, indeed, there are two things happening here. The first is that in each round, a selected subset of those clients will submit their data, right, to train the central model, right? And this is one collaboration. Another collaboration is more local, is that if these two parties have more similar data, and they should be collaborating more to train the specific model here, right? And this happens when these two weights will be more similar to each other, and therefore this model will be reinforced to these two data distribution.
Is there a data bias?
You're so smart. That's exactly what I mean. Is that, well, this bias is good and bad. Good in the sense that if this bias is shared by a group of data players, just like say non-IID data, then this bias is good. Our model can learn, our method can learn them, right? But it is bad if this bias indeed is poisoning. Then our model will try very hard to still learn that, and maybe just put this into one cluster or put it in the outlier. And let me tell you, if anyone wants to continue work on that, I'm more than happy to discuss, because we already have some thinking, but the student left, and so I don't have you to work on it. So the tricky thing is here. If you put this into one group, then this group will be destroyed, will be damaged by this poison. If you put it into kind of like a outlier, so assign the weight the same for every model, and this poison will affect all groups, right? Yeah. Okay.
I was wondering whether your epsilon rank in fairness section is independent on the assumption on the heterogeneity between all the agents. This one. The epsilon rank is independent in terms of the number of participating parties. I was wondering if this conclusion is agnostic to the heterogeneity. Is there any assumption in terms of heterogeneity, statistical heterogeneity, data heterogeneity in all the agents, all the clients?
This is a very good.
Yeah, I think because I don't have a good intuition why this, without any assumption, this one is independent of the number of parties. So could you please tell me, give me some intuitive idea about why it is independent if without any further assumption?
Let me put it this way. Empirically, I believe this is independent, but theoretically, I have not.
Oh, so this is empirical result.
Yeah, this is empirical result. Even you say you calculate the epsilon rank itself, this is a NP-half problem.
Yeah.
Yeah. So therefore, we cannot get the exact result.
I see.
This is essentially is a greedy solution.
I see.
Yeah, empirical. The reason is that if just you imagine you have a K mode situation, meaning you just have K different groups of K different group of stage of the completion of the task, right? And then your matrix is just exactly K rank, very low rank, right? K rank, right? And then now you add noise. So if you think in the intuition is that you think about it from the reverse process, right?
I see.
And then as long as the noise is not too much, that's what we intuitively came here.
I see.
But yeah, that's a very good question. I don't. Yeah, I have to think about that. Yeah, how can you mathematically prove that or give the assumption, quantitative assumption of that? Yeah.
How do you compare different calibrated data?
Can we go to the diagram near the end where you have the cloud?
This one?
Either one is fine. I'm trying to say, like, I read sometimes when you read this kind of work, you think there is like a assumed scenario when you have a almost like a valuation of the data, where you have like almost like a market for the data. I'm trying to think how this framework can be applied to a scenario like computation, allocation, research allocation in algorithm design. I can imagine for the sake of like climate modeling, I can imagine each of the client can be a model that can be updated that to improve a central a centralized model where the federated learning need is how to allocate the computation time or the update step so that you can achieve update using fewer using fewer computation.
Yeah, indeed, this federated learning, some work is just explore the cost sensitive federated learning. Essentially, what they do is that, well, for each kind, you can have a constraint, say, how many questions you can ask me, how much computation you can ask me to do, to evaluate.
And I think your data valuation here can also achieve that because you can have a fixed budget. And then once you need to get data from a certain client and you're gonna spend the budget into the data on the data that values.
Oh no, that's two different kinds of budgets. The first one is the first one in the federated learning computation framework, they say, okay, this one say I only can provide 5,000 units of computation, and whatever the unit means. Then each time it tells you, now I give you the suggested change to the model, it cost me already 1,000. So next time, you cannot ask too frequent. You can take this into account to say how to make use of this data set the best, right? This is one cost. Another cost is that in data valuation, we want to say how important these kinds data to the final model. So that would be different. It may not be correlated to how much computation it is.
But I think there is application in the climate modeling because some models are very expensive to calculate. And therefore you sort of want to calculate where you want to query, imagine that actually, if I may be mistaken, but the community Earth system model have different modules and they can have different update computational cost. And then you may not want to update all of them at the same time, and you may not need to update at the same time. So I think the two costs are the same in a way that you want to update, you want to make the informed decision of updating the unit when they are important, and then control the total cost, right?
Yeah.
Because I think the data valuation and also the fairness here is to have the accurate estimation of the value.
Yeah, the fairness there are two things here.
Is for the fairness combined the two is the
No, we do not combine two. Indeed, it is unclear how to combine the two. The first is that the compensation, I mean the reward, should be proportional to the importance of the data to the final model.
Right, exactly. That had been thinking, right? So in the system model, when you update, to be fair,
okay,
the computing allocation to a model should be proportional to the importance of that update.
Oh, okay. Wow, thank you for building this connection. Yeah.
That would be nice, right?
Yeah.
But then I just think that there makes because a lot of time when I read those kind of games, like I'm reading on Linfield games, and it's all about is a construct, but is but applied more broadly than just games or data valuation. It actually is an algorithm of allocating resources.
Yeah.
But that resource doesn't have to be money. It can be computation time.
Yeah.
So that's what I see a potential connection.
Yeah.
Or the availability of data. If you were to collect more data by knowing what was most valuable, that might be another place, right?
Right, and also I see when you talk about data poisoning, that could be that for certain model that you recognize their biases, and you can in climate system model that's also very common of understanding its impact on the final product is also something that this community does a lot.
Yeah.
There is a question online. If we can see.
How can I pick it?
Is it chat?
Yeah. How do you interpret data obtained using different calibration methods? What do you mean, different calibration methods?
If you can just speak, if you're still online, you can just speak up.
Can you hear me?
Hila, if you're still there, you can just speak, we can hear you, I think.
You cannot hear me? You cannot hear me?
Okay, so.
So the way
Can you
I
hear me?
federated learning is, you maybe talk about data privacy, but a lot of time there are also other reasons why data shouldn't leave where they are, like the transporting cost.
Yeah.
Right, so moving data, sometimes you move data, sometimes you move the computation to the data.
Yeah.
So the federated learning can also be applied when you don't want to move too much data over to centralize them to do the computation. If you can distribute the computation, that was another motivation.
Yeah, and also now federated analytics is a very hot topic. I mean, just don't constrain to machine learning models, but also some analytic results. For example, I want to estimate some statistics. Yeah, but I don't want to share the data with all of them. Yeah.
Yeah, I'm curious about the applications from your world that are most relevant here. I can see that in, for example, with census data, where you have dedicated enclaves, right? Where you want to be able to do computation on the data, but you have concerns about the privacy, right? So that's like, I can see that. I can also see that, with something like the NSF tip directory coming in, where you want to have corporations working with the academics and questions of privacy to move forward science. Like, I'm just curious, those are the things I can envision, but what are the applications that you see would be most valuable here?
Well, the typical stories about federated learning, anyway, as I said, there are very few practically deployed federated learning projects so far. The typical stories about, for example, hospitals. When you try to calculate something and each hospital doesn't want to release the information, then how can we still train a model? And financial industry like banks, like credit unions, and they also don't want to release the customer data. Then how we can still build models? Yeah. So those are the typical examples they're talking about.
If we have no further questions, let's just thank Jian again for
Yeah, thank you.